So last lecture, I think we were covering object detection, and the first topic we covered was evaluation. How exactly we evaluate a object detection algorithm, and we look into like how we can compute average precision for that, which was based on the precision and recall at different steps. So we compute like precision recall for each object bounding box which the network has predicted, right? And then we use those precision recall values to create this AUC curve, which we can use to then compute average precision, which is just area under this curve. Okay, so that was topic number one. And then I think the next topic we were looking into how we can improve the object detection algorithm, which we studied before that, which was using sliding window and using feature extraction. And we look into like a very simple solution using a CNN classifier as a backbone, which can actually perform both tasks. It can perform classification, which will tell you which objects are present. And then we had like a parallel branch, which was again like trained as a head on top of that backbone CNN, which can predict the bounding box for the object. So that way we will also be able to predict the location of the classified object. And of course, like if you have only one object present in your image, this is a very simple, perfect solution which will work. But the issue which we will face is in real world images, we won't have just one object in our images. There will be multiple objects present. And then the issue is, what if we have multiple instances of the same category, or if we have like different object categories present in that image? So this kind of approach will not work. And the reason was then the output which the network is predicting, the regression head, it will have to have like a variable sized output, which is not possible. So as a solution, then we reflected back like what was our original solution, where we were using the sliding window and extracting the features, then doing the classification. So then we talked about how we can use the sliding window, but then use CNN to extract the features. And there the issue was that if we use sliding window, first of all, we'll have to extract features from all the locations, right? As we did in the previous algorithm, and that was the biggest bottleneck. So that was issue number one. The second issue was like, we'll have to extract those features at different scales, right? We'll have to resize or reshape your image at multiple scales to create the image pyramid. So that will be computationally expensive. So those two issues, we'll see like how we can resolve those. So these two are actually covering the same 2 points. Now the solution was, what if we don't have to look at all the possible positions? What if we only look at certain positions where we are confident that objects might be present? Okay, then the idea of region proposals was discussed, where what we do is, instead of using a sliding window to actually scan the full image, we only look at certain regions in this image. And to determine these images, again, there can be multiple algorithms to do that. We can use some kind of image segmentation techniques. We can also use like key point detection, which can detect blob-like regions, like we did in Harris corner detection, right? So then the idea is, once we have these regions, then we only extract features from these regions, and we call these region proposals. Okay, so this selective search is one algorithm which was used, and I think we covered this as well in the last lecture. So today we will see like once we have all this background where we know how to extract these region proposals from a given image, then how we proceed from this point onwards. So before we proceed, any question on any topic which we have covered so far for this object detection? Because if we have understood like everything so far, then I think it will be fairly easy to understand the rest of the lecture. But if you have any doubt, any question, just let me know at this stage. All right, so I'm assuming that there is no question, no doubt. Let's move forward. So using those, okay, so a question from Joshua, will there be a poll later? So poll regarding what? No, I don't know why you asked that. Like a quiz, I mean, there can be quiz, but why are you asking? Yeah, that's fine. I mean, if you have something else urgent, that's fine. You can watch the video later, okay? No worries. Okay, so now we'll see like once we have that selective search algorithm, which can give us like proposal in any given image, how we can use that kind of input to do object detection. And the first method which we are going to look into is a region proposal CNN. So this is called RCNN. And the way this method works is you have an input image, all right? Then you will run that selective search algorithm on this image, which will give you all the potential regions or the proposals, which can be objects in this image. So you will have like bounding boxes around those regions. You extract patches from those regions, right? So you will just extract the RGB patch, and then you will actually reshape that to a fixed size. So you can use image warping for that. So because these proposals will have a different kind of resolution, different aspect ratio, right? So this is like a very tall proposal. This is like a rectangular, maybe.
Dr. Rawat, could you please repeat? The connection was lagged. It was dropped. We couldn't catch from the beginning.
Oh, beginning of this slide or?
Beginning of the slide.
Okay, all right.
Thank you.
So can you hear me okay now?
Yes.
Yeah, it's fine.
Okay, all right, great. So, all right, so what we do is, given an image, first we run the selective search algorithm, or it can be any other algorithm which can give you proposals, all right? So proposal mean it will tell you where in this image you might have some potential objects. So you will collect all those regions, so we call those region proposals, and those region proposals will have different shape, different resolution, and maybe different aspect ratio, right? So in this case, we are showing like 3 different region proposals, and you can see that the resolution is different, the aspect ratio is different, and in this particular method, what we do is we collect around roughly 2,000 of these proposals, all right? Then we will use image warping. So you don't have to like understand what image warping is. Just so the intuition is given any image, you just reshape it to a fixed size. All right, and most of the times it's just a square shaped image. So after this step, what will happen is you will have around 2,000 image patches of same resolution. Okay. Now what you do next is you use those image regions as your training samples. Right, so then they are your training samples and they will pass to like the convolutional neural network. It's a standard CNN, which you can use for feature extraction. All right, and it's the same CNN which is shared among these patches. So because these are different samples, and once you have that, you use those features to train your support vector machine classifiers. Okay, so what you're doing is instead of classifying the full image, you are classifying these smaller patches, which are these region proposals. And these SVMs will give you like a probability whether any particular object is present in these patches or not. So it's like standard classifier. Okay. Now, in addition to that classification, what you can do is you can also try to predict a regression head. And again, this is similar to like the solution which we saw previously, that you have a CNN network, and given an image, it can actually classify that object. So this first head, and the second head, last time we used that to predict the bounding box, the coordinates, right? So this time again, you will have four values, but they will not be like the bounding boxes. They will represent like the adjustment you need to make on this input bounding box, so that it will give you like the exact bounding box for the object which is present in the image. So treat this as like some kind of adjustment to your proposal, so that it covers the object very nicely. Now, again, so at a high level, if you think about this, this is similar to the architecture which we have here, right? It's exactly the same thing. So given an image, you have a CNN as a feature extractor. So in this case, you have the classifier head, which is a neural network. But in the second method, which you're discussing, we have a SVM classifier. So it's just a difference of classifier algorithm you're using. The second head, you're again using the same set of features. You're predicting the bounding boxes. But in the second case, instead of the bounding boxes, you are predicting like how much adjustment you need to make to your proposal. So in terms of implementation and like the code you have to write, it's the same thing. The only difference is instead of running that algorithm on the full image, you are running it on smaller patches. Okay. Now, what will happen is once you do that, then for each proposal in this input image, you will know which object is present, and you will have that adjustment. So you can adjust this proposal, and that will give you the bounding box as well. All right. So you are starting from around 2000 proposals. So eventually what will happen is out of these 2000, many of these proposals will be from the background, right? And some of them will be from the foreground, and some of them will be very overlapping. So then you'll have to perform some kind of post-processing, which we also performed when we were looking into bounding box object detection, right? Sliding window object detection. So there you have to perform post-processing using NMS, the non-maxima suppression. You can use the same algorithm here. And after that post-processing, you will have like very clean version of these proposals, which will give you like the exact bounding box of the object which are present in this image. So this is like a high level of this algorithm RCNN. So you might have like observed, I mean, it's nothing new. You have already seen all these things before. It's just like the strategy they use to train this network. So if you want to have a like different look of the same algorithm, so what's happening here is given an input image. So these are your proposals, and here you can see that some of the proposals or these bounding boxes are overlapping as well, and some of these are like from the background as well. So you will have proposals all over the image. The only difference is these proposals are way less than the number of proposals you will get using sliding window. Because sliding window, you were sliding like every pixel in the image, right? So if you compare that with these proposals, you are reducing the computation cost by a huge margin. And so this step is showing like each proposal, you are warping it to a fixed resolution. So this is just a rescaling. And then this rescaled image is passed to a CNN, where you can classify it using SVM, or you can use like the neural network, train it end to end. So both are fine. It's just like in this paper, they proposed a separate SVM, which actually performed better. So to start with, we'll have around 2000 proposals. And I think in this method, they use this LXNet architecture, which we have already discussed in this course. And this LXNet was pre-trained on ImageNet, 1000 classes. So they fine-tune on this LXNet on this Pascal dataset, where they use this kind of architecture for the first time. So in Pascal, we discussed last time, there are 21 object classes, and this dataset is used for object detection, right? So these are just training details for this method. So warping is fine. Then from LXNet, if you remember, like we have a fully connected layer FC7 that was like the last layer of the network, right? If you remember this from I think third or fourth lecture. So what they do is they use like all these proposals as training samples and extract these features for each of those patches. So this FC7 layer will give you a feature vector of dimension 4096. Okay, so this I think we have also covered. And they will save this to like disk, all these features. And then for each set of feature proposal, they know like what the ground truth is. For example, for this proposal, you know it's a person, right? For this proposal, at the bottom, you know it's a horse. And similarly for other proposals, you can use the ground truth and the overlap, which object this is. So then you can train for each of these feature vector, a classifier. Okay, so then bounding box regression was just to refine the location. For example, if this proposal is not perfectly over this person, then whatever adjustment you have to make it like a perfect overlap, that adjustment will be predicted using this bounding box regression. Okay, so let's go through these steps again. And so what we do is we will use a classification model. So in this case, they use LXNet. You can use any other classification model. It could be ResNet or InceptionNet. It's perfectly fine. And you next is like you will fine tune that backbone network for your target data set. So in this case, we have Pascal with 20 object categories, right? So one category is always added for the background because you will get like lots of proposals from the background as well. So you will easily assign like a negative class to those proposals, and that's why we need this. All right. So all this is fine. So this is just showing like practically if you have to do this, what you will have to do. So this one is showing, I think LXNet or any standard CNN, you will have convolution layers. Then the final layer will give you this feature map, which you will flatten, and then you will have these fully connected layers before making the final prediction, right? So when if you take a pre-trained network which is trained on ImageNet, your last layer will make 1,000 predictions because there were 1,000 classes, right? But if you have to use those weights or those parameters of the network, let's say for object detection on a different data set, let's say Pascal VOC, where you have 20 classes, right? Then you'll have to throw away like the last layer, which was actually predicting these 1,000 neurons. And that layer will be trained in the fine tuning step. And it will predict like 20 different neurons, which will be corresponding to your new data set. And the rest of the layers, you can actually load the weights, which we learned for this ImageNet data set, right? So that's like a standard way to fine tune your CNN. Now, keep this in mind that this region proposal extraction, this is not happening during your training, right? Because this is a time consuming process. And if you're going to use selective search, then you saw like there were different steps there. First, you have to do like a very fine level segmentation. Then you'll have to merge the regions to get like the coarse level regions. And then that will give you these proposals. So it's a very time consuming step, which you will do beforehand, before starting your training. So once you have done that, that will give you these proposals for all of the images you have in your data set. So then this resizing, reshaping, again, this will give you these warped or smaller regions from this image. And these are your training samples. All right. So you will start from these training samples to fine tune your network. And once the fine tuning is done, then what you will do is you will pass these patches to your CNN, and you will extract these features from FC7 if it's LXNet, like the fully connected layer. And then for each patch, you will save the features to the disk. So you will have lots of these patches. So again, this step is going to take a lot of disk space, and it's also time consuming. So for this Pascal data set, I think if you use for each image, you're using 4098 dimensional feature vector. It takes around 200 gigabytes, which is a lot. All right. So once you have those features, then each feature will have a class label based on how much it was overlapping with the ground truth. Then you know how to train a classifier. So you just take those features, you take the labels and train your classifiers. And you also know that there is no standard way to train a multi-class classifier using SVMs. So what you do is you train, if you have 20 categories, you train 20 different SVMs as a binary classifier for each of the category you have in your images. Okay. So this is just showing you a sample. For example, if you're training your SVM for a cat class, so these are all the positive patches for your cat class. And again, these are like a reshaped version, and all of these are of same resolution. Okay. And these will be your negative samples. So this is a background. So this patch or this proposal might not be overlapping with any of the ground truth which you have. So you can use that to assign that as a negative sample. And also, like if a patch is like from different class, again, that will be a negative. So if you have, let's say 20 classes in your data set, and you are training, let's say for a cat category. So all the 19 other classes will be like in your negative samples. So in total, you will have 20 categories. So you will also have a background, right? So for each class, you will have 20 different other classes from which you'll have to choose the negative samples. So then you train like binary classification for each of these categories. And so this is just showing like for a dog category. So for dog, this is the only positive sample. All the others are negative. Now, this is really interesting. We discussed that we have to do bounding box regression, right? So that regression will give you like what kind of adjustment you have to make. So if you carefully look at these three patches, so these three patches were extracted from the same image, same input image, okay? But you have a different proposal bounding box for these three. So here you can see that the bounding box is perfectly overlapping with the object category. So if you pass features from this image to a classifier, then you don't have to make any kind of adjustments to your bounding box. If you can predict like this is a cat, then you already know like the detection bounding box. You know where this cat is present in the image. So in that case, in your bounding box regression, what you will do is you don't have to make any adjustments at all. So you can say that the proposal is good. So you will just predict 0, 0, 0. So these four numbers are representing the displacement in X direction, the displacement in Y direction, and the displacement in the height and the width, right? So these are the four numbers. So in this case, you don't need like any adjustment. All of these are 0. So let's consider another example. So in this case, you can see that it's not a perfect fit. If you slide this bounding box towards the right, then it might have been a perfect fit, right? So what it's saying is it's saying the displacement in X direction. So you can see that there's some value here. And again, these numbers are normalized. So 0.25. So if you shift it like quarter of this length towards right, then it will be a perfect fit. And in terms of height and width, again, it's perfect. And in Y direction, it's perfect. So that will be your regression ground truth, which you will train against. So now these numbers are, it's not that straightforward to get these. So I think in the original paper, the displacement H, this X and Y, it was normalized with the width and the height of this proposal. All right, so in this case, if it's saying 0.25, you can see that this distance is like quarter of this width, right? So that's why it's 0.25. And the other change, I think there was these displacement in height and width. So because you can have, you'll have to normalize these because each proposal will have different resolution, right? So to ensure that your network predicts like a values in the right proportion, I think they used a log scales for these. But yeah, I mean, that's not important. Those are like finer details. It's fine. But the idea is like you have to predict like what kind of adjustment you will need to make this a perfect proposal. Okay, so let's consider like one more example. Again, this bounding box is like much bigger than what we need for this cat. And in this case, when the cat is just at the center, right? So height is the H position is the Y position is fine. The X position is also fine of the center. So dx and dy, we don't need to change anything, but the width is slightly bigger than what we need. So this negative 0.125, it's again a normalized value. It's saying that we need to shrink the width of this bounding box by this much amount. Okay, then we will get the perfect bounding box. So these are like the ground truth which you will train against for the second head, like which is the bounding box regression. Okay, so that was your RCNN, and this was like I think the first paper using these CNNs to perform object detection, and it is very popular. It has been used widely, like not just in this object detection thing, but lots of other areas. And people have tried like to extend this to videos as well. So, but you can see that the idea is fairly simple once you know the basics. So any question before we start looking into like what are the issues which you have to face with this RCNN algorithm? Or if anything is not clear to you and you want me to repeat that. All right, so that was a good solution, but let's see like what are the issues. The first issue is you can see that you will have multiple proposals in this image, right? So you will have roughly 2000 proposals. So what will happen is most of the time your proposals will be highly overlapping with each other, right? And during training, what you're doing is for each of the proposal, you are passing that image, that warped version to the CNN to extract the features. So it means like for each image, you will have around 2000 forward passes, so which is a lot. All right. So a solution is instead of passing like these proposals 2000 times into the CNN architecture to extract the features, can we just use a single forward pass? Okay, so that's the idea. And that way, if we do that, it's like roughly reducing your computation cost by a factor of 2000, right? You don't have to do that for all the proposals. So that's issue number one. Now, the second issue is what we are doing is for each proposal, we are passing it through the CNN, extracting the features, saving it to disk, and later on, we are using that as a feature to train the SVM classifier. So that's not like an end-to-end learning. And we have touched upon this topic before as well. So if we extract the features beforehand and train the classifier later on, then there is no direct connection between your feature extraction and your classifier training, right? Those two are separate steps. So what's the drawback? The drawback is you might be extracting some features which are not important for your classification task, right? But if you have an end-to-end learning where you jointly extract the features and classify those features like in a single step, such that when you're updating the weights of your classifier, you're also updating the weights for your feature extractor, then that's really important. What will happen is your feature extractor will extract only those features which are important for the classification task, right? And that's what we are going to do. So we are going to do like an end-to-end training to avoid this issue from RCNN. Now, the third issue is the training pipeline is very, very complex, right? As you saw that you have the image, you first have to perform selective search, you get the proposals, you'll have to perform warping to those proposals, run it through the CNN, extract features for all the proposals, right? And then load those features again to train a SVM. So it's a very complicated pipeline, not during training, but also during testing. So the question is, can we avoid that? And again, this is like the same solution which we saw for issue number 1. So we'll just have to do single forward pass for each image. If we do that, then we don't have to do feature extraction for like all the proposals separately. So let's see how we can do that. And the solution to that is fast RCNN. Again, this is a paper from the same authors who proposed RCNN. And it was like the upgraded version of RCNN. It was faster, therefore the name fast. So what they did is they tried to address those two issues which we just discussed. So instead of having multiple passes for each proposal, we'll just have a single forward pass. Okay. And instead of training a separate classifier, so in that case, they were using SVM. They were just classifying the extracted features from the CNN so that they can train the full network end to end. All right. So let's see how they did this. So given an input image, instead of extracting the proposals and then passing each of those proposals to the CNN, you just pass this image to your CNN network. Okay. And this CNN network will give you some kind of features, intermediate features. So they extracted the features from the conf5 feature map. Again, this is the AlexNet architecture. All right. So this conf5 feature map will have certain shape, X, Y, and Z. So X, Y is like the resolution of the feature map. Z is the depth, which corresponds to number of channels in that particular layer. Now, what we do is, instead of applying the proposals in the input in the input image, we'll apply those proposals on this feature map. All right, and again, it's the same step. You will take each proposal, do the warping, and make sure that after warping, the resolution of all these feature maps is exactly same. So instead of doing this step on the image, we do this on the feature map. So this saves us a lot of time because now we don't have to run this connet or the CNN feature extractor on each batch. We just run it once and extract the features from this feature map. So that's optimization number 1. Now, to do this transformation, and this is like, I think the crux of this ROI pooling, it's very popular. We will discuss this in detail, how exactly this ROI pooling is done. But at a conceptual level, this ROI pooling is exactly doing like the image warping, which we are doing at this image level. All right. But that was before your network, so you don't have to train that. But this ROI pooling, we have to train it. So we can't perform an operation which is not differentiable. So that's why we need ROI pooling. So then we'll see that this ROI pooling, this layer is differentiable and we can easily train this end to end. So once you have these ROI pool regions, you convert these to fully connected layers. Again, this is just feature flattening. And instead of saving the features to disk and later training an SVM, what you do is you directly pass this to like a neural network or a linear layer, right? And classify it. So instead of a separate classifier, you have this classifier head just on top of this fully connected layer. And again, the bounding box regression on top of this same fully connected layer. So you don't need to do this separately, just integrate it in the same network so that you can do backprop when you are extracting the features while learning the classification. So this network is like addressing all those 3 issues which we discussed. And the only component which is not clear, I think at this time, is this ROI pooling, and we are going to look into that. Okay, so that was our solution number 1. We just have to pass like image only once. That's the solution number 2. Instead of a separate SVM classifier, we are training it jointly. And that's solution number 3. All of this is like end-to-end network. Now let's look at the ROI pooling layer. So you take your image, you extract the feature map. So this feature map will have certain shape. Now what you do is you take the bounding box of your region proposal, and instead of mapping that to the image, you will map that on this feature map. So for that, what you'll have to do is you'll have to perform some kind of scaling to this bounding box. So it's like a direct projection on the feature map. So if your, let's say, input image is of shape 512 cross 512, and the feature map has shape, let's say 64 cross 64, right? So that's like 8 times reduction. So then what you will do is you will perform the same 8 times reduction on this proposal bounding box and put that over this feature map. And then the ROI-Pooling layer, what it will do is it will take features from just this region and convert them to like a fixed shape of feature map, which will be passed to the fully connected layers. You have the flattened features, that's the softmax classifier, and that's the bounding box regression, right? So apart from this ROI-Pooling layer, any question you have, anything which is not clear? Okay, so let's see how this pooling layer works. So input image, that's the feature map, that's the projection. So what we do is on the projection, we divide that region into a grid of H cross W. And this H cross W is like the shape which we want to pool these features as a transformation, right? So this is like the output resolution we want for all the proposals from this feature map. So the shape of this image is 3 cross 800 cross 600, right? And the feature map has a shape of C for channels, then height and width. So in this particular proposal, you create like these many grids. Then what you do is, and again, this is like H cross W, that many cells. For each cell, you simply perform a max pooling operation from this input feature map. So in this cell, there will be like multiple pixel values, right? Or multiple feature map values, multiple activations. So what you will do is you will take like the maximum of those values and just put that value in this particular cell. And you will do that for all the cells in this grid. And that way, the output of all the proposals will be of a same shape, this C cross H cross W. Right? So this is like your ROI-Pooling layer. And as I said earlier, because we have to train this whole network end to end, this has to be differentiable. And we already know that max pooling operation is differentiable, right? The gradient flowing back from this particular pixel location will go to the pixel or the activation which was picked for this cell, okay? So yeah, that's the same thing. It can backpropagate. So now let's see like some sample example. So that's your input image. And this was your proposal. So the proposal shape is 200 by 145. And the feature map is 16 cross 16. So what we will do is based on the scaling of like this image and this feature map, we will also scale this proposal and put it on top of this feature map. All right. And then it will give you like the locations of these bounding boxes. So then you will see that you will get some fractions like this, these odd numbers. So there's 6.25, there's 4.53, the height and the width, right? So you will have to just quantize these values. So if it's 6.25, we will just make it 6. 4.53 will make it 4. And that way it means that in the height dimension, you will have 4 pixel values, 1, 2, 3, and 4. You will just ignore this region. And in the width, you will have 6 values, 1, 2, 3, 4, 5, 6. Okay. So you're just converting your float values to normal digits to make the quantization. So then this red boundary is like the original proposal which you got. But after quantization, this orange region here, that will be your region which you're going to use for your ROI pooling. Okay. Now, in this case, you can observe that. So this was the region in the input image, right? So what you're doing is your ground truth bounding box was like this, or your proposal was like this, but you're shifting towards right. It means that you are actually taking some extra values from the left, right? And you are going to miss these values. Okay, and that's perfectly fine. I mean, it will have some information loss, but it's not that crucial. Okay, so the blue region here is like the information you lose, and the green is which you gained. So green is like you're getting extra context, and the blue is like you are missing on you might be missing on the content itself. Okay, then that will give you a 4x6 ROI region. This is called region of interest, right? Because you have like the height of this proposal as 4 and width as 6. And now what you have to do after that is, let's say you want to reshape all your proposals from a feature map to shape 3x3. All right. So then what you will have to do is you will divide the crop feature map according to this dimension. So if it's 3, then you will try to divide it by 3, but it's not perfectly divisible. So we'll just ignore the rest. Again, so this was quantization number 1, when you have to map your proposal bounding box onto the feature map, right? And this is the quantization number 2. So this is like when you're actually performing the pooling operation. So in both scenarios, so in this scenario, you will gain information, the context information, and then you will lose information. In the second one, you can't you can't gain information, but you might lose information, right? So what will happen is, if you look at like the height of this region of interest, it has four pixel values, but the target needs just 3, and 4 is not divisible by 3. So this last row, you will have to let it go. So that's like the information loss. And in the width, like you can see, you can easily take like 2 pixels at once. And what you can do is you can perform a max pooling operation on these 2 pixels. So whichever activation is higher, you will just pick that. Same with this, and same with like all the locations. You just have to perform max pooling. Okay, so all these is like when you combine this together, this is called ROI pooling. And this is like just one sample feature map, and this is your lost information. So one solution for this is this region of interest align, and this was I think proposed later, not in this work, and it's useful when you have to actually not perform object detection, but when you have to perform semantic segmentation. Because if you look at the problem of object detection, you don't need very fine boundary, right? You just need a bounding box. So even if you lose this information, it doesn't make that much of an impact. But the case where you have to perform a semantic segmentation, like the exact boundary, then this is very crucial. And later on, we will see when we look into semantic segmentation, we'll discuss the same method, but not for object detection, but for semantic segmentation, then how this information loss is very crucial. And there we will see like how we can fix this information loss using ROI align. So this is another layer similar to ROI pooling. Okay, so another important thing here to note is, so the features you are getting at this particular location, right? It doesn't mean that to get this activation, you only considered features from this location, right? To get this activation, if there are like several layers in your CNN, then the actual region which you use to extract this activation, it will be much bigger than the actual projection of this bounding box on this input image. And that's called receptive field. So receptive field is something which like to get a pixel value or pixel activation here in the feature map, what region of the image is required. All right. So we will not discuss that in detail, but I think you should know the intuition or the idea behind that. So when you are performing the convolution, so let's say you have a 3x3 kernel, right? So when you put that kernel on this location, so it takes like values from all the neighboring pixels as well, right? Some kind of correlation, and then it predicts value for this particular region. So to get this activation, it is looking in the neighborhood as well. And this is just one layer. Now think about like how you got this pixel value in the previous layer. So it might have looked into the neighborhood, right? So you can see that just in 2 layers for getting this pixel value, you are actually looking at a bigger region. So if you'll have several layers, I think 6 or 7 layers, it might be that to get activation map, you're looking at the full image. It's just that you're paying more attention on the center pixel, but it's not that you are ignoring the neighborhood region. So that's called receptive field. And it's usually after several layers, it mostly covers the full image. All right, so that's another important point here, why this like information loss is not that important in object detection. Okay, so if we compare the performance of this fast RCNN with RCNN, so training time here, this is 84 hours, and it's reduced to just 9 hours. So the speed up is like the training speed up, it's almost 8 times. Now, even on testing, I think there is a huge gain. So you can see that testing one image, it takes like 47 seconds in RCNN, but fast RCNN, it's like a fraction of a second. So it's like 146 times improvement. So the reason why we got this improvement is it's mostly because we don't have to train a separate classifier, because that requires like extracting features, saving on disk, and then loading those features again. So that was too time consuming. And also like, again, passing the image through the CNN, just in a single pass, that's another contribution. But effect of that is not prominent during training. It's more prominent during testing. Because during testing, then you don't have to perform that forward pass for all the proposals. You just do for the whole image once and just extract the features and do classification and regression. And that's why you have a huge improvement here. And in terms of performance, if you look into mean average position on this particular data set, so it's slightly better in 1%. So it's not that huge. But if you look at this performance gain based on the computational complexity, it's huge. Okay. So that was fast RCNN. Now, before we look into the problems of fast RCNN, do we have any question?
Professor?
Yes.
In ROI-Pooling, we are converting 4x6 to 3x3. So here, how we are converting 6 columns to 3 columns? We are considering every 2 neighbor column and we are dividing.
Sorry, Sunil, I barely hear you. So can you please type your question?
Voice is audible now?
Yes.
Okay. So, Professor, in ROI-Pooling, right, when we are converting now from 4x6 to 3x3, so how we are converting 6 column to 3 columns? For every 2 columns, we are every 2 neighboring columns we are considering, and we are dividing it by 2.
Yes. So this ROI-Pooling, you have to perform max pooling operation.
Oh,
right?
okay. Okay.
So then based on like what's the shape of your input feature proposal and what's the shape of your output feature map, what you want, you can actually determine like how many pixels you need to generate one pixel, right? So in this case, the input is 4x6, the output is 3x3. So you'll have to do like the width parameter separately and the height separately. So let's talk about the width first. So you need 3 pixels here, right? But in the input you have 6. So what you can do is you can convert like 2 pixels to 1, and then you can easily get 3, right?
Yeah.
So you can perform max pooling on these 2 pixels. Whichever activation is higher, you just use that.
Oh,
Same
okay.
for this, same for
Okay.
this.
Okay, I got
And
it.
let's talk about the height. So we were lucky, like when we were computing the width, then it perfectly divides the output, right? But in the height, it's not the case. So if you divide 4 by 3, you will get 1 point something, which is not like a perfect number. So then you'll have to lose some information. So we just disregard those pixel values. So then in this case, you're just transferring the values because there is just one pixel. So it will be the max one. So is it clear?
Yeah, it's clear now.
Okay, great.
Thank you, Professor.
Any other question? All right, so let's see like what are the issues in fast RCNN. Now, as I said before, so for fast CNN, you're still using the selective search for the proposals, right? And getting those proposals during training time, it's fine. I mean, you can spend that time, do some parallel processing, use a lot of computational resources to perform segmentation, get those proposals and save onto disk, right? But what about test time? During test time, you want it faster, right? You don't want to spend time on just doing that proposal computation. So the testing time which was reported, it doesn't include these region proposals. I mean, it was assumed that we already know these proposals and we counted like the testing after that. But in fact, like this region proposal is like computationally expensive. So the solution is, what if we don't have to extract like these region proposals beforehand? Can we extract these regions inside the network? And that was the idea behind faster RCNN. Okay, so we want to use like the CNN architecture to predict these proposals instead of like any external algorithm. And again, this is like from the same authors, the paper in third series. So the idea is you take the image, pass it through the CNN, get the feature map, and this is like your normal path, which you already know. Once you have the proposals, you apply those proposals on the feature map, and the rest you already know. You perform classification, you perform regression on those proposals, right? So this is the new part. And this is called a region proposal network. So what it does is, instead of using the proposals from like any external algorithm, it uses the same feature map to determine where the objects might be present. And this saves the computation cost by a huge margin. Okay, so the idea is we use the same CNN. So these weights are shared. These are in fact the same network architecture. And we use like these feature map to predict these proposals. So now let's see like how this region proposal network works. So the input to the region proposal network is this feature map. And the output we want is these bounding boxes. Okay. Now what we do is we take the feature map, and again, we're going to use the sliding window. Right? You have seen like the sliding window has been used so many times in so many different contexts. So it's a very powerful idea. And they are again relying on this sliding window to get the proposals. So what we do is we have this feature map, right? We'll have some kind of window and we will slide this window on this feature map. Now, this is not very expensive. The reason is the resolution of the feature map is not as big as your input image, right? It's pretty small. So you will not have like a lot of positions to scan from this feature maps. But what you do is you actually use different aspect ratio and different sizes of these sliding windows. So for each location, you will have multiple, we call these anchor boxes. So these anchor boxes are like the window which you will use to extract the features, all right? So I think there were 3 different scales. Scales mean like how big your sliding window will be, and 3 different aspect ratios. So the aspect ratios were, the first one is the square, right? Then this is a rectangle, which is vertical. And this is another rectangle, which is horizontal. And then you have 3 different scales. So again, the same square bounding box, but a bigger scale. Similarly, you will have bigger scales for these 2. So in total, you will have 9 anchor points or anchor boxes. So for each location, you will put like 1 anchor box and extract the feature. Right now, to extract the feature, again, you will perform that ROI pooling and extract the the features in the same dimension. So this is like 256 dimensional long. So again, you will have this ROI pooling between this, and you will use those features to predict like whether this proposal is a positive proposal or a negative proposal. Right, and then you also have these 4 key coordinates. This is again a regression head, which is like the adjustment you will have to make to this bounding box. Okay, so once you train this, then what will happen is, in total, I think there will be a lot of locations here, more than 2000, because you have 9 different anchor boxes, and let's say you have 100 different positions or 1000 different positions. So that will give you like maybe 9000 different proposals. So then you will have to classify those, but out of those, you will only get like some of the positive proposals, right? Which is this classification head. So this is just showing like the anchor boxes you have. So 3 different scales and 3 different aspect ratios. And keep in mind that I mean, you have this fixed anchor box, but you do have this regression head on top of this. So there might be some adjustment to that proposal. Okay, so this I think we have covered. Now, based on that output, you will know that which are the positive positive proposals, which are the negatives. So you will use the positive proposals as your region proposals, and then use them to extract like the features from the actual feature map. And this is the same process. So the only addition is like this region proposal network here. So this is like a quick summary for RCNN. We first have to extract the regions, right? And then we classify those regions. Apart from classification, we also have this regression head to refine that bounding box. Fast RCNN, we still have the proposals from the from an outside algorithm, but we don't have to slide like our windows on the input image. Instead, we slide that window on the feature activation map, so that we have to only do a single forward pass, and it will be an end-to-end network. Faster is even better. So we don't use external proposals. We generate those proposals inside the network. So then it's like end-to-end, starting from the extracted proposals. So these are the 3 papers, and I think these are very, very highly cited, very used a lot in computer vision, as I said, like in most of the problems. And I think if you are planning on working in this area, you should go through these papers. It will be really helpful for you. All right, so that's it for today. Any questions? Okay, so there is a question from Furkan. Instead of bounding boxes, can mask be implemented for those proposed regions? Okay, mask like for instance segmentation. And I think that's a very interesting question. And answer to that is like a subsequent publication from I think the same authors. And that's called Mask RCNN. And if you're interested, you should look into that. So what they do is, after having, let me go back further. Okay, so there what we have is we use like these proposals. So they added like another head to that, which gives you the segmentation boundary, the final boundary. So instead of this bounding boxes, you will get like a separate region or a perfect segmentation mask for each of these objects. So that's like on top of the same algorithm. So the paper is called Mask RCNN, if you're interested. Okay. Any other question? So we are right on time today, and that's good. So I have a couple of things regarding the programming assignment. I hope that programming assignment 2 is going well. So we will release like the programming assignment 3 in a couple of days. And so for the programming assignment 2, there were some changes like to the language which we have used in the document which we shared. So for some of you, it was confusing, and thank you like for pointing that out. So we have tried to correct that. So you can check the announcement for that. Hope like it's more clear now. And that was for programming assignment. And so yeah, we have already released like the solutions to your assignment 1 and your midterms. If you have any questions, just let us know. Oh yeah, one more thing. So this week you will have one extra homework assignment. I think I released it yesterday or the day before that. It will be due on Friday. And we are doing that because we don't want you to be like too busy like towards the end, because you will have to finish your programming assignment 3 and you have to finish your course project, and you will also have to prepare for your final midterm. So we want to finish like all these homeworks beforehand. Okay, so if there is no other questions, I think a question from Furkan. For programming assignment 2, what will happen for those who has already submitted the assignment regarding the KNN function? Oh, okay. So you're saying that you used an existing algorithm or an existing implementation?
Yes, I submitted actually last week, and I used like built-in function.
Okay. So no worries. That's fine. You can implement again and share the assignment via email, and that should be fine. Okay. It's good that you are proactive, finishing on time. All right. So if there is no other question, we can end it here.